into cloud server. Okay. So now, let us go to what we had left. So we had argued the following. What we had argued was, suppose we have an atmosphere where at some level, which I can call z equal to 0, I have rho O, PO, and TO are the density, pressure, and temperature in the atmosphere. And there is a blob, and um, the pressure, density, and temperature inside the blob is Pi, rho I, and Ti. And there is a perturbation because of which the blob is displaced in the vertical direction by a distance delta z. And in a new position, the atmospheric density is P naught, pressure P naught prime, pressure is, rho naught prime, pressure is P naught prime, and temperature is T naught prime. And at this point, you have the blob, since, okay, the blob is of a different size now. And so the pressure inside will be now different. The pressure inside is Pi prime, rho I prime, and Ti prime, pressure, density, and the temperature. Okay. And what we had said was the blob is sufficiently large that the surface area to volume ratio is small. And so the heat, the heat inside it cannot be, oh, Bharati is there. So the heat inside it cannot be removed to outside very efficiently. And so I say, and so what I say is that this process, timescale over which it covers this distance delta z is called T dynamic. T dynamic, yeah. Hi Bharti, yeah. T dynamic is the time taken to move this vertical distance delta z. Then there is T thermal, which is the time taken. Oh, something happened. Okay. Is the screen back?
Yes.
Okay, so this is the time taken. Oh. For restoring thermal equilibrium. That is, if I move the blob up, the temperature inside will change because of expansion and so on. And if I leave it like that, it will take certain time for this to come in thermal equilibrium with the surrounding, and that is T thermal. And then there is tau thermal, and then there is tau mechanical, which is when I move it to a new situation, the pressure and all is different. So it expands or contracts to make the pressure equal. And tau mechanical is the time taken for restoring pressure equilibrium. Is this okay? This I explained last time itself.
Yeah.
Okay. Now we work in the regime in which the T dynamic, okay, or that T mechanical, just a minute. Yeah. No, not tau, T mechanical, tau mechanical is much less than tau dynamic, which is much less than tau thermal. What it means is, within the time it takes to move from this lower position to higher position, this time is so large that by this time, the pressure inside is able to adjust itself so as to remain in as equal than outside. Is it okay? That is, it happens. I mean, if the time dynamic is more, it means it is slow. It takes more time. So the blob raises in such a quasi-static way that at every point of time, the blob keeps expanding and keeps the pressure inside and outside in equilibrium. Is that okay?
Yes.
Yes.
Okay. However, the blob is so large that for it to come in thermal equilibrium with the surrounding takes a long time, much more than the time taken for it to go this distance delta Z. Okay. Now, this inequality implies that P inside equal to P outside always, which means specifically Pi is equal to Po and Pi prime is equal to Po prime. Are you with me?
Yes.
Okay. And what does this imply? This implies that no heat exchange implies process is adiabatic. And this implies that Pi by Pi prime is equal to rho I by rho I prime to the power gamma, the adiabatic index. Okay?
Yes.
Okay. One further says that let us assume that at the initial state, Pi was equal to Po because of pressure equilibrium anyway. We also say that rho I is equal to rho O. That is only in the initial level. Rho I is rho O and Ti is To. So in other words, there is a portion of the gas which is indistinguishable from rest of it. But some spherical region I have isolated and moved it up. Is that okay? Because at this level, pressure, temperature, and density all are the same inside and outside. Is that okay?
Yes.
Yes, sir.
Okay, fine. Now, let us just okay. So now let us now go to the next step. And that is okay, fine. So here we had these two together imply that rho I prime by rho I is equal to Po prime by Po to the power 1 by gamma, because the pressure inside and outside is the same. So whether it is PI or PO doesn't matter. Okay?
Yes.
And now I can say that I take log of both sides. I have log of rho I prime by rho I is equal to 1 by gamma log of Pi prime by Pi. Okay? Now, I say that rho I prime is equal to rho I plus delta rho I, and Pi prime, oh, in fact, I can put it as PO. Why did I write Pi? Because Pi is same as PO. So PO prime is equal to PO plus delta PO. That is, as we move from Z to delta Z plus delta Z, the pressure of the atmosphere changes by delta PO. And the density inside the blob, because of the expansion or contraction of the blob, will change by delta rho. And so I assume that delta Z is sufficiently small so that delta rho I is much less than rho I, and delta PO is much less than PO. And so log of rho I prime by rho I is equal to log of 1 plus delta rho I by rho I, which is rho I by rho I. Okay? Okay?
Yeah.
Yes.
Right. Now, similarly, I will do the other side. I will have log of PO prime by PO is equal to log of 1 plus delta PO by PO is equal to delta PO by PO. And so I have from all this, from this, and this, I have delta rho I by rho I is equal to 1 by gamma delta PO by PO. Okay? So this is how, when the external pressure changes, this is how the density changes. Fine. The next step is, so this is, okay. Now, the next step is the pressure outside. I say that the atmosphere is assumed to be an ideal gas. Which is what we have been doing. We have been discussing, like conditions under which this ideal gas approximation works. And hence I have PO prime by PO is equal to rho O prime by rho O into TO prime by TO. I mean, because, P equal to NKT and N is rho by M and so on. So this is for the ideal gas. And this implies that rho O prime, okay, I'll go in the next one. This implies that rho O prime by rho O is equal to PO prime by PO into TO by TO prime. Okay, fine. So now we have two things. Let me just go back to this expression. I had rho I prime by rho I is equal to Pi prime by pi to the power 1 by gamma. Okay. And since pi and pi prime are same and rho I and rho O are the same, this implies that pai prime by rho I prime by rho O is equal to PO prime by PO to the power 1 by gamma. Are you with me?
Yes.
No. Okay. Yaril, Snigdha?
Rho I equal to rho 0 because at the initial stage they are the
Initial
same.
stage, exactly. Exactly.
Uh,
Okay. And now, so I have these two equations. Okay. So I have rho O prime is equal to rho O T naught TO by TO prime PO prime by PO, and rho I prime is equal to rho O PO prime by PO to the power gamma. Now, what is convection? What is convection is if in the new position, rho inside is greater than rho outside, then the blob will sink and go back to initial position. Is that okay? Because there is not enough buoyancy. The density is higher, so it will sink back. Is that okay?
yeah.
Now,
Yeah.
however, if rho I is less than rho O, then by buoyancy, the blob will move further up. And this is called convection. Okay? So that is in other words, although initially the rho I and rho O are the same, it is an unstable equilibrium. You push it slightly up, it starts moving up. Okay?
Yeah.
Fine. So now, this is here. And so now we just have to put these things together. So it means that rho I prime less than rho O prime implies that rho O PO prime by PO to the power 1 by gamma is less than rho O TO by TO prime PO prime by PO. Okay? Is that okay?
Yes.
Okay. And so this means that, so now you see something very interesting. I have reduced the entire relationship of the atmosphere parameters without any reference to what is happening inside the blob. So from here, I know that if I know the condition of the atmosphere, I know convection takes place or not. And so this will imply that PO prime by PO 1 by gamma minus 1 should be less than TO by TO prime. Okay. And so I do the expansion, I will have 1 plus delta PO by PO to the power 1 by gamma minus 1 less than TO by, yeah, sorry. So it will be is less than 1 by 1 plus delta TO by TO. This implies that if I do a Taylor expansion, it means that 1 plus 1 by gamma minus 1 delta PO by PO is less than 1 minus delta TO by TO. And so this means that 1 by gamma minus 1 delta PO by PO is less than minus delta TO by TO. All right?
Yeah.
And what it says is, this implies that here you have to be a bit careful. And the reason suppose you multiply throughout by minus 1, then it will be 1 minus 1 by gamma delta PO by PO delta TO by TO. Since you are multiplying by minus 1, the inequality will flip.
Reverse.
Okay?
Yeah.
But there is another thing. You see, delta PO is always less than 0.
Yeah, decreases.
Yes. And when it goes up, it will expand. So delta TO will also be less than 0. Okay?
Yeah.
It means that actually I can write it as 1 minus 1 by gamma mod delta PO by PO is less than mod delta TO by TO. All right? And so this implies that delta PO by delta TO is less than PO by TO into gamma by gamma minus 1. Okay? Is that all right?
Yes.
Now, here I can write it now as minus dPO by minus dTO, because mod of a negative number is a negative of that number. And now here, of course, I can cancel minus 1 and plus 1. So what it means is, I need delta PO by delta TO less than PO by TO, gamma by gamma minus 1, which implies D of log of PO by D of log of TO is less than gamma minus 1. All right?
Yes.
Yeah.
Okay. Now, this is a very interesting thing. What it says is, depending on the pressure-temperature relationship of the outside region, it will decide whether convection will take place or not. Okay? So it means that if I plot LNPO versus LNTO and some value of gamma, this is so. Okay? Now, what I do is, this is the, and okay, so this should be Okay. So for example, if I have something like this, or for example, suppose I have in fact, I should convert this into the other one. Okay. Suppose the actual pressure temperature relationship, okay, was like this in the atmosphere. So this has a slope of gamma by gamma minus 1. And hence, this will lead to no convection. Okay?
Yeah.
On the other hand, suppose the thing were like this, then I will have convection. Okay? So now what you do is, suppose I have a situation where, okay. Okay. So suppose I have a situation where the situation is like this. Okay. Now, what I will do is, wait, I don't know whether it will be correct. Got the correct thing or not. DP, that's okay. DP by, yeah, that's correct. Yeah. Now, this, okay, the slope, if the slope is, note that the higher altitude preserves temperature decrease. Here we have dropped the, okay, just a minute. Rho I less than rho O leads to convection. So this leads to convection. Okay. Means that if at any point in atmosphere, if this is here, right for convection. Okay. So this, here no convection takes place. And for convection to take place, what I need is,
Sesh,
hmm?
let's say I have the green line, right? Which has the slope that is less than what we've calculated. Does that mean the balloon will keep going up forever?
Sorry, what is it? Volume?
I mean, does that mean the blob will keep going up forever?
No, no. That's what I was coming to. So suppose I have a situation, yeah, that's what I wanted to actually put it here. Suppose I have a situation where the actual pressure temperature relationship is something like this. Okay. Suppose I have an atmosphere where the pressure temperature relationship is this, that is, at low temperature, the pressure is increased very rapidly and then shallows it out. Then what happens is, when the gas is present here, okay, no, I just want to convert it into Z. Then this will be, just a minute. Just a minute. Okay. So now, if suppose this is the situation, then there is no convection here. Okay. So if there is there is, if the outside gas in this situation, then a slight perturbation will take the convection up. Okay. Now, let us have the other situation where we have the other situation. I mean, this is my Lakshman Rekha. And it is like this and like this. Now, what happens is, here at this point, the condition is there for convection. And at this point, it is not convection. Okay. Now, suppose the temperature goes like this, temperature versus Z. Okay. Suppose it at some point, the temperature is here and it increases at another point Z. Now, what can happen is, see, this is what happens in Delhi when there is this pollution. What happens is, the surface gets very cold. Okay. So as you go up, whereas here, the temperature is warmer. No, that is not what. No, I want to, just a minute. I want to convert it into as Z. Just hold on. No? I will just tell you. Temperature is here. Okay, so let me just try it out. Okay. So now, suppose for example, at a level of something like 15-20 meters above the ground. I mean, I think this is okay, but I mean, just take it with a pinch of salt, but I'm just constructing an argument here. Suppose during this, some 10-15 meters above the ground, the pressure does not change substantially, right? The pressure does not change substantially, whereas the temperature can. Okay. Then what will happen is, as you go to the higher features, so if suppose the temperature is low, I had an argument for this. I mean, basically what it happens is called temperature inversion in the atmosphere. Here, for example, okay, so this is a convection, this is not. So what happens is, somewhere in just next to the surface, this condition gets met. So the air starts moving. But since as you move up, the proximity to the ground changes and this temperature becomes different and it comes to this situation. So what happens, although the air starts moving up, when it comes here, there is no convection. And so this air hangs around here. So when you have pollution, then with pollution, the whole thing goes up, but it cannot go up, but some hangs around at some low level. And this is what happens when, I used to see that in Ahmedabad when I was doing a postdoc. Those days, there used to be double-decker buses. And in Ahmedabad, in autos, they used to use kerosene mixed with petrol to reduce cost. But when petrol burns, kerosene does not burn, and some portion of unburnt kerosene gets ejected. And now what happens is, in the evening, when the surface gets cooler, then the whole temperature profile is such a way that somewhere around the deck of the double-decker bus is a place where temperature inversion happens, and all this kerosene fumes will condense at that height. So if you actually sit on the top deck, your eyes will start watering. I just wanted to make this argument a bit watertight. There is actually another way of doing it. I didn't want to do it because it's very complicated. I mean, this is the one with, let me just give you the result. Okay.
I have one doubt.
Ah,
So in the green plot on the left-hand side,
ah.
so the no convection, that occurs even before the second point, right? Like this slope that becomes more than the red one.
No. What it says is, at any point in the atmosphere, depending on this curve, you see,
Yeah.
so if suppose you have a high, this one, at this point, depending on this is meant or this is wet, there will be convection or no convection.
Yeah, I get it. Like, like you have marked the second point, no convection, right?
Yes.
But there could be another point even in the middle that has a slope bigger than gamma by gamma minus one. Only then it will turn, right?
Yeah, absolutely. So what is happening is all these things will collect here and all these things will collect here.
Okay. Is
Yeah,
that the
you're right.
point
You're
where
right.
temperature inversion happens?
Yeah, that is how temperature inversion happens.
Okay.
Yeah, Harish, you are right. I mean, that's a better way of putting it. So the question is not where it intersects. I mean,
Okay.
so if suppose you have a profile like this, and this is my reference slope. So I put this reference slope. Yeah, this is a better way of doing it. Yeah, thanks. Wait. So now if I take this and keep it here, then convection happens. Similarly, convection happens here. And till here it happens. But beyond this, the convection does not happen. Do you understand?
Yes.
Yeah.
So, like I take this small, this thing to compare the slopes, and I will move this wherever I want to know whether convection, here. So I keep it here. The convection happens. Convection happens. Here the slope is equal. And then the slope of that increases. There is no convection. So in other words, all these points from here onwards will start moving by convection. All these points will start settling down. And this is actually what happens. So this is a good way of, so all these pollutants here will go up, but at some level, these will come down and then condense at some level. And that is where the pollution is very obvious. And this is the origin of fog. Why is it there is fog? That is because when there is sunshine, the surface gets heated and the whole temperature thing is such that the equilibrium position for this moist air is somewhere slightly high. So that is why early morning you won't have fog. But just as the sun starts rising, there will be a fog which will start coming in Delhi. Is that okay?
Could you repeat the thing about fog?
You see, what I'm saying is, before sunrise, the surface is cold. Now, when the sun rises in winter, the surface starts getting heated up.
Yes.
And just the adjacent layer gets heated up, and then the convection starts setting up.
Yeah.
And it starts moving up. That's where the fog comes up in the atmosphere. Previously, it was all as dew on the surface.
Yeah.
Okay. I mean, this is a very crude, this one, but this is the basic thing which happens. I'm just toying with one thing. There is another way of doing this. Wait a minute. This is a bit complicated and I can understand because this is from Landau and Lifshitz. It's very interesting result he has. And the result he has is a condition for convection. Is just a minute. See, because if I have to do that, I have to, should I actually do this because it will involve entropy of the blob and so on?
Yeah, we can do it.
Okay, so I will prepare it next time, and this is a much better way, I think, because it will actually tell you. See, here it is just telling me about pressure-temperature relationship, but it is not telling me in reality where is this satisfied and where is not satisfied. It just says that if the pressure temperature relationship is this, then convection will happen or not happen. On the other hand, is that here, I just took it. Incompressible fluid. Energy flux. So there is another, I mean, in a similar way, but with entropy consideration, one can derive the result that minus of dt by dz. Remember that this is temperature generally. Okay, so minus of dt by dz should be less than the acceleration due to gravity divided by specific heat at constant pressure of the gas. Now, this I feel is a much better thing, because now what it says is this. It says that suppose I draw this. Now, this implies that dt by dz is greater than minus g by cp. All right?
Yeah.
Okay. Now, suppose as before, now this is t and this is z. And as before, suppose this slope refers to slope of minus g by cp. Okay. It says that if I have okay, so I mean, now I'm sort of aware of what Harish was pointing out. Let me not do it on that, because it looks as if it is okay. So let me put it this. So it's like this: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. So now suppose I have the temperature profile of the atmosphere as like this. That is, temperature falls very steeply. Okay, with Z. Then what happens is, here the dt by dz or minus the, I don't know here. I mean, this negative sign. Yeah, okay. So now this dt by dz here is less than minus g by cp. Right? Because it's negative. I mean, it's a higher slope, but it's a negative direction.
Yes.
Okay. So here, I will not have any convection. Okay. Now what I do is, at the base, I start heating the system. Okay. Then what happens? Gradually, this becomes something like this. No. If I heat the system, the temperature should... No, what am I doing mistake? Just a minute. So let me just do it again. So I have minus dt by dz should be less than g by cp. Oh, sorry. This is for stability. I'm sorry. It's the other way around. From this, we easily the condition is satisfied. The condition that the convection is absent is this. Convection occurs if these can... sorry. It has been the other way around. That's where is the problem. Sorry. I will just remove this. You know, for some reason, lots of authors put the condition for convection not to take place. I don't know why. I thought convection is such a beautiful thing. Okay. So, fine. Okay. For convection, what I need is minus dt by dz should be greater than, it should be greater than g by cp. Okay, yeah. Okay. And now so it means that dt by dz should be less than minus g by cp. Okay, so now let us look at it. So I have this is minus g by cp. Now dt by dz has to be greater. It means that while decreasing, if it is a gentler slope, so if for example, at some okay, so let us, as before, I have this, and suppose my temperature gradient is like this. Okay, T and Z. So I take this and keep it here. I find that throughout this, the slope is what? Greater or less? Hello?
Yeah.
No, this slope is greater or less than this one?
A much negative slope.
Yeah, it's a less negative slope, so it is greater.
Yeah.
Okay. So in this case, I will have no convection, because this is the condition for convection. You see, dt by dz is greater than minus g by cp. Note, dt by dz is less than 0. Okay?
Yeah.
On the other hand, suppose I have a situation where this one slope is like this. And then if I take this and compare, now this slope is less, it is more negative. And so this condition is satisfied. Okay. So here dt by dz is less than minus g by cp. It is more negative. Are you with me?
Yes.
Yeah. And now that argument which I was giving will work. Now suppose I have this one, some water, and let us assume that it is at the same temperature. I mean, water or air or whatever, because I have done it for only gas, but okay. So this is how it's roughly at the same. Suppose you take a cylinder of gas. Roughly in the cylinder of gas, the temperature is the same at all Z, right? And if I now start, so this, so this is the reference slope I need. Clearly, in this case, there is no convection, because dt by dz is 0, whereas this slope is minus g by cp, and 0 is greater than minus g by cp. Okay?
Yeah.
Is that all right?
Yes.
Okay. Now I start heating the system. What happens when I heat the system? The portion which is just next to the z equal to 0 starts getting heated. So this can get modified to like this. Okay. And once I do that, if I compare here the condition of convection is satisfied. And so the air which is just next to it starts moving up.
Sesh, what is that here?
That is the height from the bottom.
Okay.
Okay, so at Z equal to, suppose I'm heating some cylinder of gas from below.
Okay.
Okay, at Z equal to 0, it is getting hotter.
Okay.
So this goes up. So here, far away, it's still the same. So the slope becomes like that, and here the convection is set up. And so the material from here starts moving up. On the other hand, yeah, this is interesting. So on the other hand, suppose I heat it, but even after heating it, suppose it has gone like this. Then although the temperature below is higher than the temperature above, the slope is not sufficient to induce convection.
Yeah.
Okay, so what it says is, see, generally you will think that if suppose there is warm air below and cold air above, there will be convection. It is not. The warm air below has to be sufficiently warm to give the enough gradient for it to be pushed up.
Yeah.
Okay, so this is an important lesson here. Okay, and okay, now let me argue for that fog. Now, suppose I have, suppose this temperature over here at next to it is low, and this is high, or this is, yes. Okay. So suppose, yes. So suppose in winter, the temperature which has is something like next to the ground, it is very cold and it slightly increases above. Okay.
Okay.
Then here no convection takes place. Right? Now what happens? This surface gets heated and this goes up. Portion next to the surface gets heated, but far away from the surface, it is still like this. So the thing becomes something like this. Okay. Next to the surface, it gets heated, but it does not convey to the higher reaches. All right.
Sesh, can you repeat?
Yeah. So what I'm saying is, suppose initially the temperature is something like this of the atmosphere above the ground.
Okay.
Okay.
Like, why does the temperature increase with Z here, like before the sun?
Oh, I mean, it's okay. It's because the surface is very cold.
Okay.
Okay.
It's less than the temperature at the top.
Yeah, or you can even keep it same. There's no problem. What you can do is, even if it is sort of same.
Okay.
Now, what
More or less
happens
the same.
is, the moment the sun rises, just like so the sun rays do not get absorbed directly. It is only the reflected one which gets absorbed. Okay. And so when the sun falls on the ground gets slightly heated. And so the temperature profile becomes something like this. Okay. Now what happens is, Now let us compare this. Okay, so now let me do it. Suppose it becomes like this. Maybe I'm just exaggerating it, but that's okay. So now if I compare it over here, here the condition for convection is satisfied.
Yeah.
So the thing starts moving up, but the moment it comes here, after this, the convection condition is not satisfied. So the portion here is higher than the density of the surroundings in this region. Whereas in this region, okay, so what happens is, so since the thing is equal over here, in this portion, there is convection, and in this portion, there is no convection. As a result, these things come here and these things go here, and at this level Z, things start piling up. And this is exactly how the pollution and smog and all happens.
Okay.
See, that is why generally the flights which get affected by fog are the ones which are early morning, not when it is dark. So once sun rises, this fog starts coming up and the visibility starts becoming poor. Okay.
One solution to this is like lowering the temperature at the top, right?
Pardon?
Which we can't do, like,
What is it?
one
Sorry.
solution to this, Can you hear me?
No, it's breaking. Can't tell me. It's breaking.
Even now?
Yeah, now tell me.
Okay, so one solution can be like lowering the temperature at the top such that the gradient is, the smart of,
No. We are
this relation
talking about a
holds.
large ground here. I mean, suppose it's an airport.
Yeah, that was just a fictitious solution.
Okay. Okay. Yeah. So what I'll do is next time, you want me to derive this?
Yes.
Yeah.
So this will involve very interesting, thermodynamic relations, Maxwell's relations, and so on, and to derive this. We'll do that.
Okay.
Okay. Okay. Chalo. Good. Bharti, hi. Are you getting it? Okay. Chalo. Bye.
Good night.
I would like to ask something.
Yeah.
Like, so teams do like we have MS teams, so that would take a lot of people, and like there's no restriction on that.
Pardon?
For the 20th, Feb, the National Science Day.
Yes.
Can we use Teams on that day?
Oh, Teams is a pain, man. Teams is a horrible
pain.
pain.
A lot of people.
Oh, Teams is a horrible pain. I don't know why government institutes use Teams. It's horrible.
Everyone here use Teams. So.
It actually, I will tell you, the problem is Teams, hogs memory.
That's it. Yeah.
That's the problem,
All right, like then, if the number exceeds,
maybe it is not 100, but it is 300. I will just check it.
All right.
No, because I have a paid thing for Zoom.
Yeah. Yeah, 100 is the basic account, I guess.
So I think I have a paid one. So it is, I think, 300.
All right.
There is no problem.
All right.
Okay. Sure. Bye.
Good night, Sid.
Bye.
Good night. Snigdha, you're very quiet.
Yeah.
Snigdha.
Yeah.
What happened?
Nothing, sir.
Okay.
Bye, sis. Good night.
Bye.